So welcome back, everyone. Let's keep our event. I would like to invite Professor Sergio Bumpi to be the session chair for this presentation.
Thank you. Good morning, everyone. Good afternoon, wherever you are.
Okay.
Okay. Let's start this presentation. This invited talk will be given by Professor Hussam Amrouch. Let me introduce the speaker for this talk. Dr. Hussam Amrouch, who is a professor at the University of Stuttgart in Germany. He is the chair of Semiconductor Test and Reliability, the STAR research group. And he's also, for many years, has been and still is a research group leader at the Karlsruhe Institute of Technology, also in Germany. Dr. Hussam Amrouch earned a PhD in computer science in 2015 from the KIT in Karlsruhe with distinction, summa cum laude, and soon after, he led the Dependable Hardware Research Group at KIT. He has, over 140 publications in journals and prestigious conferences. And he's very actively engaged in the research in emerging technologies and machine learning as an application, and machine learning for CAD. And, he is covered in his research many areas of the computing systems. From semiconductor physics, devices, circuit design, then on top of that, computer architecture and computer-aided design issues. He serves as an associate editor of the VLSI journal, the Integration Journal. He's a guest and reviewer of many journals and review editor for Frontiers in Neuroscience. He has served in committee of many prestigious conferences in those areas. So it's a pleasure here on behalf of the IEEE Circuits and Systems Society chapter in Rio Grande do Sul, who has organized this workshop. It's the 13th edition, and I welcome back, even virtually here. And I remember in 2019 you have been speaking here for the CAS e-micro, School of Microelectronics event. So welcome back, Hussam. It's a pleasure for all of us here in Brazil, all those organizing the CASS. This is being broadcast over YouTube, and we'll get questions at the end of your talk through the YouTube channel. So please, the audience, feel free to address questions to the speaker as he goes speaking, and in the end, we'll collect those questions and go for the question and answer. Again, the floor is yours, Hussam. You can share your screen, and very good to have you here in the CAS Rio Grande do Sul workshop.
Thanks a lot, Sergio. Many thanks for you, for Guilherme, who invited me to here. So it's a great pleasure to be with you again. Unfortunately, virtually. So I still remember my trip to Brazil, visiting you and others, talking in 2019. So yeah, I'm glad to be with you, at least virtually. And thanks for having me here. I have already shared the screen, so I assume hopefully all good. So, and I'm going to start. We are, as engineers, always obsessed nowadays by the amazing improvement that's coming from deep learning. We are always obsessed about the significant improvement in the accuracy that we are obtaining from our deep learning models. Many things and many applications, many breakthroughs would not be possible in the last, or we could not dream in the last couple of years without the breakthroughs from the deep learning and machine learning models. But we need that we remember and we be careful that's all started when the specialized hardware and the invention or the breakthroughs in the hardware and the accelerators that came from Google around 2016, the so-called Google TPU. And many, how to say, inventions in the last couple of years happening in the area of neural processing units in order to accelerate deep learning, training, inference. So this is a very active area from both sides, algorithms and system level sides, how to say, as well as from the underlying hardware. However, today I'm going to share with you and draw your attention about one enemy that we need that we be very careful and find against when it comes to deep learning and neural processing units. It's temperature. Temperature, in fact, I call it the unseen enemy for our future chips, and this is why we need that we be careful about it and we think proactively how we can solve it and deal with it, which is quite different challenge that we used to do with our traditional multi-core systems. And that's actually in summary, the main topic of the talk today. First, we are, again, as an engineers, always obsessed in increasing the efficiency of our system. Our hope and our dream is if we increase the efficiency of the systems, we will gain more and more saving. However, this is not always true. If you think about using a very efficient car, you would hope that at the end of the year you will save lots of money because the driving or the cost per driving is very little. But that's not actually the case. If we have very efficient car in which the cost per drive is very little, then we will start to drive our cars more and more often. And at the end of the year, we will actually spend more money for the maintenance and guaranteeing the reliability and the maintenance of our car. And those hidden costs will compensate, if not canceled out, most of the gain that we have obtained at the first place from the saving. Environmental problems, which one of the main driving force behind inventing efficient cars, will start to increase because the efficiency is so high, everyone will start to drive his car more and more often, and environmental problem will start to increase instead of decrease. And that's actually very well known in the automotive industry. In economy, this is known as Juventus Paradox. He observed more than 100 years ago in England that after the invention of the steam engine, which became, or at that time it was a breakthrough and was very efficient compared to other engines, Juventus observed in England that the total consumption of coal was keep increasing instead of decreasing. How could it be after the technology made the process very efficient? Then the total consumption start to increase instead of decrease. How could it be the efficiency did not provide us with saving? Many years later, this became as Juventus Paradox. Juventus Paradox, whenever the technology makes a process very efficient, the gain, the large demand, the large demand and the demand and the increase in the demand, the large increase in the demand for that resource will compensate, if not canceled out, most of the obtained saving in the first place. And this is well known in economy that efficiency not always lead to saving. How this is really related to technology and silicon and chips and microprocessors and what we used to do in our community. In fact, I see a very straightforward relation. If you think about the transistors efficiency has been tremendously improved in the last couple of decades. More than 1000x improvement we have obtained in our transistors and energy switching energy in the last 4 to 5 decades. Because the efficiency of transistor became amazingly good, the demand behind transistor increased. Nowadays we have chips with more than 10 to 20 even billions of transistors. And how this could happen? That's actually because we were able to keep scaling down our transistor geometry and our transistor feature sizes in order to provide this large and serve this large increase in the demand for transistor and packing more and more transistor within the same chip die, we had to scale down to below 10 nanometers. Nowadays, Samsung and TSMC already producing 5 nanometer chips, and the 3 nanometer is already in the near future roadmap. However, when we reach such fundamental limits in transistor scalings and we reach such an atomic level, the reliability of our systems and our transistors cannot be guaranteed anymore. And to ensure safety and to ensure and fight against uncertainty, we have to include larger and larger safety margins and larger guard bands, otherwise the reliability cannot be ensured. And such guard bands will compensate, if not canceled out, most of the obtained saving that we have obtained from the efficiency when we scale down the transistors in the first place. And this, in my opinion, one of the manifestation of Juventus paradox, but in technology instead of economy. Let's remember and let's take a look where we stand nowadays in technology scaling. If you think about it, the blood cell is around 100 micrometer, and even coronavirus that's causing all these problems nowadays and the pandemic and the reason why we are meeting virtually today, it's just 100 nanometer, which is amazingly small. But we as a humans, we are able to create transistors that's by far even much smaller than the coronavirus itself. As I have just said, the Samsung devices, the 7 nanometer, already in the production since 2019. And even they have announced that the 3 nanometer transistors is coming soon in 2024 or 2023. And the only reason for such a delay is due to the pandemic nowadays. But let's remember that the DNA and the protein itself is just 1 nanometer. So we are so close to such fundamental limit in scaling. However, as usual, whenever we are reaching such a fundamental limit, there is breakthroughs should come. And we need that we remember when before talking about the breakthroughs, what's actually the reason for the breakthroughs, the need for such an emerging technologies and breakthrough. It's not only the minimization of the feature sizes of the transistor, but actually there is another problem that's coming along the aforementioned, how to say, minimization problem. It's actually the voltage crisis, the voltage wall. If you think about the transistor, it's actually, you can abstract it as a switch between on and off. What really dictates and determines the speed of the transistor is the steepness of the curve. If we could make the transistor much steeper and we make the subthreshold swing much smaller, we could actually achieve the same on current, but at much lower voltage. What that really means, it means we can keep clocking our circuit at the same frequency, at the same clock, at the same performance, without any loss in the performance, but at much lower voltage. But what is the problem? Why can't we arbitrarily make our transistors as steep as possible? Well, the so-called subthreshold swing has a fundamental limit. And in semiconductor physics, this is very well known since the invention of the transistor, or almost since the MOSFET came. This is actually attributed to the so-called two capacitance in series and the voltage drop that will happen always in between. If you think about your MOSFET transistor and the field effective transistor in general, it's actually you have the insulator capacitor and then you have the underlying MOS capacitor. And the subthreshold swing, it's actually always 60 millivolt per decade multiplied by a constant factor. Let's call this constant factor lambda, which is known, or typically it's called as a body factor. Now this lambda, it's coming from these two capacitors in series, as you can see here, and that's actually 1 plus a positive value. And that means this lambda always larger than 1. In the best case, could be 1. As a result, you have the subthreshold swing. It's always fundamentally larger than 60 millivolt per decade. But let's think about it for a second. Where we stand in technology scaling nowadays, TSMC more than 5 years ago, they have already achieved the 64 millivolt per decade. So if the 60 millivolt per decade is a fundamental theoretical limit in subthreshold swing, and we are already in technology scaling almost at the 64 millivolt per decade. And let's remember what we have learned in the last few slides, that we also at the 5 nanometer and the 3 nanometer is coming soon. That means we are reaching at the same time two problems, two crises. One is from the technology scaling and the feature sizes minimization itself, and one from the voltage scaling itself. So whenever we have very small feature sizes. At the same time, voltage is not really scaling. What do we expect? We expect very high power densities, very high temperatures. From here, you can start to predict why temperature is a hidden problem and also is getting much larger in the upcoming technologies. Temperatures is very well known to be as the key source for failures in semiconductor devices. Temperature, once it increases, it impacts our devices, our circuits, our systems in two ways. One is short term. That means in the next few milliseconds, microseconds after the temperature has increased, the reliability and the resiliency of the circuits goes down. If you don't include enough safety margins and timing guard band, timing violations will start to appear in your circuit because the clock frequency becomes unsustainable. Similarly, when it comes to memory, if you have the temperature or the temperature increases, what will happen? The memory and the SRAM memory becomes more and more susceptible to noise. Therefore, data corruptions, the data integrity of the memory cannot be ensured anymore. So at the short term, once the temperature increases, lots of problems start to appear in the circuit. So temperature is not good in the short term, even almost immediately or instantaneously. On the other side, if you have a chip that's suffering from elevated temperatures and excessive temperature, excessive heat for a long time, aging in the circuit and the transistors start to become larger. That means the lifetime of the chip cannot or they'll become smaller and smaller, and the reliability of the chip for the long term, let's say after 5 years or 7 years, cannot be guaranteed any further. Therefore, temperature is bad immediately for the chip as well as for the long run because the lifetime of the chip becomes smaller. The temperature is a result of two things: having voltage that's not scaling. Because the voltage is high, the power is high, the power density becomes high, and the reason, remember, voltage is not scaling, but also the feature sizes is keeping scaling and reaching atomic level. Temperature is in fact the unseen enemy for technology, and literally the unseen enemy. And as have been said, the unseen enemy is always the most fearsome. Why? Because once it's here, it's too late. In my opinion, nowhere in technology is that more true than when we look at chip's temperature. If you think about it, how you could really fight against the temperature and how we can really predict and protect your chip against temperature if you cannot see the temperature at the first place. What you get your silicon die with a package with a heat sink and a heat spreader and heat sink on top of it, yet you really need to predict precisely your temperature, how it's evolving in order to protect against its effect. In order to predict the temperature accurately, you need to predict the power accurately, you need to have the entire floor plan, and at the end, all those estimations might not be as accurate as possible, and the crisis, a hotspot could emerge during the runtime somewhere across your chip, causing a temporal or even a permanent failure. So therefore, temperature, if we don't see it, is very hard to fight against it. And again, the key question is how we can really see the temperature underneath, how we can really clearly measure the temperature that's happening during runtime in our chips. In order to solve this problem, we have built the first infrared camera, the first thermal setup that can measure precisely the thermal map, the entire thermal image for modern processors without any layer in between. That means you have your infrared camera measuring directly the infrared emissions of your silicon die directly, which allows you for the first time to see how the temperature evolves in those complex modern chips in order to analyze it at the design time and understand how the temperature can really evolve at the runtime. This gives lots of insights for the reliability management, even for chip designers to understand where they have to locate their thermal sensors and how many they have to put. This is an image of the thermal setup where the infrared camera measures directly the chip temperature. We see here the Intel 8-core chip without any package, any heatsink, and any heat spreader, like a naked, silicon die, and then the camera itself measures directly the infrared image. However, it's not always easy to see the temperature. In this example, I gave you and show you a solution in order to see the temperature at the large granularity at the chip level. But the temperature is not always to be seen. When we think about the transistor itself, not from the macro level, and let's look at the micro level, we have also another type of problem, by far more difficult. Revealing temperature is not always easy. When it comes to advanced transistors, such as what we see here, the FinFET transistors, the temperature and the current density and the power density inside the channel of the transistor itself becomes very high, which means that even though you measure the temperature of your silicon substrate, of your silicon die, and that temperature still looks cool or cold relatively, the temperature inside your transistor channel is so high, but it's so encapsulated, so trapped inside your transistor, in which it's very difficult to escape to outside and then be captured. And that means your temperature or your transistor is almost heating up from inside, but you cannot even observe or measure that. Your sensors inside the chip still tell you the temperature is cold. It's like a room temperature, 27 degrees, like you see here in this analysis for 14 nanometer FinFET technology calibrated with industrial measurement data. We see how the temperature near to the drain is so high, yet the substrate of the transistor, the silicon itself, is relatively cold. That die, again, if you measure the temperature of it, it will tell you it's still cold, but the transistor channel itself goes 100 degrees above the ambient temperature. We have done the analysis also for more advanced transistors, such as the nanowires. We can see even with the nanowire, the temperature problem getting even more challenging. And this is very well known and so-called or often called or referred as self-heating problem in transistors. When we have such a 3D confined structure where the channel is surrounded by the gate in order to have better and better electrostatic control, what we have that the generated temperature from the channel is facing more and more difficulty to escape to outside and be dissipated. We see here in the nanowire, due to the very high confinement and the 3D structure of the gate all around, how the temperature near to the drain is getting so hot that it's not able to escape to outside. We have also done the analysis for advanced nanosheets, which is the next generation after the FinFET technology and expected to replace FinFET at the 5 nanometer and below that. Also, the problem is challenging there, even it's more than the FinFET itself, because the sheet itself facing the metal sheet, for instance, facing more difficulty to dissipate the heat compared to other sheets. All in all, in summary, the temperature in advanced technology nodes is getting more and more challenging at the micro level and the macro level. Within the transistor itself, generated heat facing extremely difficulty very high difficulty and extreme difficulty in order to be able to dissipate and go outside due to the advanced 3D structure, quantum confinement, and many other effects that's happening at the extreme feature sizes like 5 nanometer and below, or in general below 10 nanometer, where quantum effects becomes dominant. On the other side, when we go to the larger scale, we also have the problem that temperature, especially in advanced heterogeneous structures, we don't understand very well where the hotspot will be evolved at the runtime and what's actually or where actually the problem could appear, and therefore we cannot really fight against. And if we want to be just very pessimistic and just fight against temperature and worst case of temperature, we will definitely lose lots of the efficiency gain that we have obtained at the first place from our technology scaling and from adopting advanced technologies. How this is really related to AI chips and deep learning, the main motivation of my talk and how I have started? Well, it's all very well connected, as you will see in the next couple of slides. First of all, deep learning models and breakthroughs in the accuracy of many AI applications made many of our, how to say, dreams that we could not even dream in the last couple of years became possible. But such breakthroughs in the accuracy of models and algorithms and systems would not be possible without other kind of breakthroughs in the underlying hardware. In fact, many of those improvements in the accuracy attributed to the very tremendous increase in the complexity of deep learning models. Nowadays, models consist of, I don't know, many hidden layers, and you have millions of parameters and sometimes billions of weights. But in order to train such models, it's not easy to do it with your traditional hardware. This is why breakthroughs in the underlying hardware was really necessary in order to make those complex model, training those complex model feasible. And that opens actually the door for deep learning to get more and more accurate. This started all with Google TPU 4 to 5 years ago, which is deployed in data centers, started with the inference, and nowadays the Google TPU version 2, 3, 4, all of them able to support even training, speeding up the training tremendously, making complex models feasible. Also, we see now these accelerators and those AI specialized hardware. We see them already in our even mobile devices. Most of the mobile devices from Samsung, from Huawei, already including even Apple, nowadays everyone, including already an specified engine to accelerate deep learning models. We see also that such neural processing unit also at the extreme edge, which as an example, the Google HTPU. But we have a problem. In such, how to say, complex systems, and if we take a look at the picture here, which is from the ISCA 2017 from Google, TPU, the first version, and what we can observe that the large portion of the chip is actually dedicated for systolic MAC array. The systolic MAC array consists of, in this example, 64,000 MAC unit. And this 64,000 MAC unit all confined in a very tiny problem, a very tiny area, which is 24% of the chip. And this is really a problem because this will consume huge power confined in a very small area and will lead very quickly to excessive heat generation. But you can say, where's the problem? We have a cooling solutions. We have our fan, our heatsink, which will make sure that the heat is dissipated effectively. That's actually not really true because we have an inherent problem in the cooling solution. They are actually inefficient. If you think about it, you have to cool down the entire chip, putting the fan, whereas your fan and the large heatsink, whereas actually the hotspot is located only in one place. In order to investigate this problem, we have actually done a complex multiphysics simulation using an ANSYS, which is a finite element simulator, commercially or commercial tool, ANSYS for very advanced heat simulations. And we have done that for the entire system where we have this systolic array mimicking the TPU, and we analyze the temperature under the maximum and the highest air cooling thermal convection. And what we have observed is, and the technology that we use, it was 14 nanometer FinFET technology calibrated with Intel data. And what we have observed that the temperature of the systolic array will go beyond the maximum temperature of 100 5 or the critical temperature 105, and we can see at the nominal voltage of around 0.7 or at 0.7 the temperature will reach above 120 degrees, which is indeed critical. And whenever even we boost a little bit the voltage and we go to 0.8 volt, the temperature of the systolic array will even exceed the 130 and the 140 degree. And no surprise because, it can even reach the 180 degree. There's no surprise of that if we look at the power density. The power density, the total power consumption of those 64,000 Mach units, and remember, multiplier is always very power hungry. And if you put 64,000 of those multipliers working simultaneously, jointly, generating huge power confined in a very small area, 24% of the entire chip, then the power density can easily reach 200 watt per square centimeter and even nearly to 300 watts per centimeter if you boost your voltage. Such a massive, such a very high power density with the limited capability of the air, even at the maximum thermal convection, will lead to temperatures that can exceed the critical temperature. Is that really true in reality? Is that what we have observed in our simulations really match what's happening in data centers and other companies? Actually, interestingly, that the Google TPU has caused the problem, as it has been announced by the Google CEO himself. He said during the announcement of the I think the version 3, the Google TPU version 3, he said, these chips are so powerful that for the first time we have had to introduce liquid cooling in our data centers. That shows that the problem that's coming from the neural processing units and the problem of packing and putting thousands of Mach units in a very small confined area. But let's take one step back and think about the problem in the traditional cooling and why we need some emerging cooling solutions. Traditional cooling will try to cool down the entire chip using, traditional fan or maybe even water cooling. But remember, this is a little bit inefficient or maybe largely inefficient. Why? Because actually you are trying to cool down the entire chip even though your hotspot is located in a very small area. Yet you are trying to cool down the entire chip. Remember, for instance, if you take a look here, you have 30% of your chip reserved for the on-chip SRAM memory, which is not really critical because it typically has a very low power density compared to the systolic Mach array. What is the solution? Actually, if you think about it, the solution should be straightforward if we could invent a cooling that can be localized. If you could cool down the chip only where it's needed, instead of cooling down the entire chip, which will cause efficiency loss because you are paying cost for the cooling for everywhere where it's actually needed only at a specific and certain location. If you could cool down your chip only where the hotspot is located and only when the hotspot is emerging, you could actually do much better job. You could actually cool down more efficiently your chip. And that's actually one of the need for the emerging cooling solutions. And in this regard, I would like to introduce one of the many breakthroughs in the material science that's happening, not just recently, actually in the last decade, but maybe we in our community, we don't hear often about it. It's called superlattice thermoelectric device. And the thermoelectric device is an old concept. Actually, Peltier discovered this phenomenon more than 100 years ago. And thermoelectric devices are very well-known devices to provide a controlled source of cooling. The problem always with the thermoelectric devices is actually the thickness. Bulk thermoelectric devices that commercially exist since many, many decades actually very thick. So therefore, using them and large in general. So therefore, using them and integrating them in the traditional cooling solutions for our microprocessor and IC chips was always not a good choice because they would isolate the heat from the die itself to the heatsink itself, and this will cause a problem instead of solving the problem, unless you pump them with a huge current to overcome that. But then it becomes very, very inefficient. The breakthrough that came in the last decade is actually through inventing a way where you could fabricate the thermoelectric devices in a way that the ultra thin, they call them ultra thin film or superlattice. The thickness of them is just 50 micrometer, for instance. And by integrating them within the chip die, we are able actually to put them where the hotspot is generated, and then we can cool down only the hotspot and paying the cooling cost only at that location. Now, in this case, what we will have, for instance, we have done this analysis for the thermoelectric device where the hotspot is located at where the thermoelectric device is located on top of the thermal hotspot. And we can see here how we are able to suppress actually the temperature of the hotspot, and it goes down from the critical temperature of around 124 all the way down to around 108. And that shows the effectiveness of the thermoelectric device in order to, the superlattice, to be precise, the superlattice thermoelectric device in order to cool down localized hotspot. In this analysis, we have used a multi-physics simulations, and in this example, we were able to dissipate or to suppress even a thermal hotspot of around 200 watt per square centimeter. Now let's connect all the dots and go back to our original problem, the neural processing unit. How we can really manage the temperature of the manage the temperature of the neural processing unit? What are the different means and options that we have in hand? First of all, we have precision scaling. Remember, the problem is coming from the multiplier, and the multiplier is a very power-hungry component. But the multiplier itself could be a different precision. What really, determine which precision we need is the accuracy demand of the neural network model. We know that neural processing, the neural network models typically they don't really need very high precision. Some of them they need, some of them they don't need. So we have a knob in our hand which is related to the precision of the multiplication, the precision of the arithmetic unit itself. If we decrease the precision, we could actually reduce the dynamic power, we could reduce the power in general of our fundamental block, the MAC unit, and as a result, the entire systolic array, the entire MAC array, power will go down, hence temperature will go down. So the first knob that we have in our hand is the precision scaling. On top of that, we have our traditional knob, which is frequency scaling. Reducing the frequency, no doubt, will reduce the temperature because the power is related linearly. But reducing the frequency means a loss in the throughput, as we will see soon. Finally, we have this nice new knob that I call it advanced cooling solution using thermoelectric. Nowadays, it's commercially not there, but many labs and some companies even start already to demonstrate that. There's no reason why we don't imagine and envision this could be possible in the near future, and there's no other place to be true more than the neural processing unit due to that big challenge that comes with them with respect to power density and on-chip temperatures. So to summarize, we have the precision scaling as a knob. Reducing precision allows us to improve or mitigate the temperature with the cost of accuracy. Frequency scaling allows us to reduce the temperature and the cost of throughput. Finally, advanced cooling and thermoelectric device will allow us definitely to suppress temperature, but at the power cost, because you have to power it on. You have to feed it with lots of current and power in order to create this nice cooling effect. So it's not cheap, it's actually expensive when it comes to power overhead. However, the key is, instead of we focus only on a single solution, why don't we focus on hybrid solution? Why don't we reduce the precision a little bit reduce the frequency a little bit, apply advanced cooling a little bit, and then such a hybrid solution can open door for us in which accuracy loss of our deep learning model is minimized, power overhead due to cooling is minimized, and then throughput is maximized and temperature is maintained under certain thresholds. And that's actually what I'm going to demonstrate and tell you about how the thermal management of neural processing unit could be achieved using those different knobs that we have in hand. Let's start with a key question, how we can evaluate all those things together. In fact, there's a large gap. We talk about deep learning models, which is something at the high algorithmic system level. We talk at the same time on something like superlattice, which is complex multi-physics simulation. And then we talk in between about power density, which necessitates a full chip design in order to be precisely estimated. And how we can really evaluate all those different pieces coming from different abstraction layers all at the same time. Let me show you how we built that and how this framework could be realized. We started from the system level where neural processing units can be trained. PyTorch in this context has been employed. We trained different neural networks, for instance, for the dataset ImageNet. And then, in order to explore the impact of precision scaling, we had to do quantization. And the quantization is a famous, powerful technique for neural processing unit in which, after you train for your floating point precision, which is a high precision that's required during training, you can apply quantization. In fact, the Google TPU version 1 was for 8 bits, but the models were trained for 32 bits floating point. And many studies show there is a minimum and very marginal loss when we really reduce the precision and quantize from the original 32-bit level all the way down to 8-bit. But we ask ourselves another question, how about if we reduce the precision further and further? Of course, we are not the first to ask this question. Many other studies investigated, and it's a very hot topic nowadays about investigating the impact of quantization in deep learning models, on the impact of them on the accuracy, because it's very well known will give a very nice reduction in the power. So let's start from the highest level. We use at the system level the PyTorch. It allows us to train the neural network, to quantize the neural network, to get the inference accuracy. So everything with respect to precision and accuracy would be studied there. Then we need to answer the next question, how the power density will look like. And to answer that, we have actually to do the full chip design, and we need to do the traditional chip design, how to say, and using the traditional sign-off tools for power, for timing, and this will give us how to say accurate temperature, because accurate power, because we can get the area and the floor, the area, and then the power accurately after the layout, and this provides us with the power density. So to estimate the power density, there's no magic. You really need to do the synthesis, the chip design, the floor plan, the power, the area, and then you could estimate the power density. And then we have done that for 14nm FinFET, and the underlying model card was calibrated with available data, publicly available from Intel 14nm devices, for more how to say insights about the calibration process and the library characterization to achieve that, all provided in our paper. So then we reach the next level. We want to understand the impact of heat, the impact of cooling, and all those we have studied using the multi-physics simulations from ANSYS, which is, as I said, commercial tool that employs finite element methods to study sophisticated heat simulations process. And there we have implemented the cooling from thermoelectric devices as well as the baseline heating effect. So all those studied there. Now, once we have those three different pieces, we can actually integrate all those ingredients together, and we perform design space exploration to trade off temperature, power, overhead, cooling cost, neural network accuracy, and throughput. All of those we can study now. Once we have this, I would say, multi-layer framework, we can start from deep physics all the way to accuracy of deep learning. And I will show you a few examples in the next couple of slides. Let's recap. We have frequency scaling, very powerful, very well known, traditionally to fight against temperature. The cost is the throughput. Precision scaling, very well known, accuracy will be dropped as a cost. Advanced cooling, not very well known, it's emerging cooling solution. The cost of it is additional power overhead. We studied the hybrid solution in order to minimize the overheads. We can employ actually precision frequency scaling, where you combine the precision scaling with the frequency scaling. What would be the cost, throughput, and accuracy? Finally, you could actually combine all of them and do precision scaling, frequency scaling, as well as emerging cooling and thermoelectric cooling, which is referred to as TE, and then you will get, the throughput, accuracy, power as a cost, but that would be very powerful, as we will see soon. Let's take a look here. No surprise, reducing the frequency or reduce the temperature almost in a linear fashion, because the power is linearly impacted by the frequency. However, the throughput also linearly will be degraded. So temperature will be reduced with frequency scaling nicely, but the cost will be very high when it comes to the throughput. And remember, with deep learning, we really like high throughput. When it comes to the precision scaling, you can see here in the green line, it shows the accuracy drop for 20 different neural network models have been all of them analyzed, and then the accuracy or the average accuracy has been reported. We can see here for the 8-bit, the accuracy is quite high, no surprise, but then 7-bit is not too good, and then it starts to really drop very quickly. While the temperature is reduced, the accuracy is not maintained anymore. So therefore, the precision scaling, even though it could be perceived as a nice technique to reduce the temperature, however, it's actually a little bit limited. It has a limited capability, and at the same time, the accuracy can be severely impacted. Now, when it comes to the superlattice thermoelectric device, we can see how the temperature is dropping or reducing very nicely. More than 40 degrees can be reduced. Of course, the cooling cost is high, can reach 40%. Well, there is a trade-off. If someone really wants to reduce the chip temperature from 120 degree all the way down to 40 degree, no free lunch, as we used to say, and a cost of around 40% must be paid. Now, the superlattice thermoelectric device, I want to mention that it actually allows us to open a new door, because a new door for a new design space exploration. So if we put the thermoelectric device on top of the MAC array, we could actually cool down only the MAC array there, and that allows us to not reduce the frequency a lot, allows us not to reduce the precision. And now, based on the deep learning model and the neural network model, we can actually figure out how much we have to reduce the frequency, how much we have to reduce the precision, how much cooling cost we have to pay in order to satisfy a certain requested temperature constraint. This is an example of the new design space that we can explore when it comes to neural processing unit temperature management. You see here we have those different trade-offs: temperature, power, overhead, throughput, etc., precision, and then based on the requested temperature constraint could be 420, for instance, in data centers, or maybe 75 degrees for your mobile devices or for each device. Then based on that, you could figure out the Pareto optimal solution. This is an example about the effectiveness of such intelligent cooling on the TPU. We measured here, or we focused on the efficiency as a frequency multiplied by throughput divided by the power cost. We can see here how the efficiency this is the normalized efficiency, and we have different examples: ResNet, neural network, and BGG11, and mobile net, just as an example. The paper has all the results for the 20 different neural network models. Temperature constraint was here quite tough. It was like a 70 degree, which is really, really tight. And remember, originally you start from almost 120 degree or above even 120 degree. What we can see here, how for some models that can tolerate precision scaling, we are actually able to reduce or increase the efficiency by, let's say, around 3x, while the accuracy drop is very small. For other models, where, for instance, this mobile net, the tolerance for the precision scaling is almost zero, so we have to stick at the 8-bit, and then we have to pay the cost differently. So this is the beauty of having such larger design space to be explored, which will allow us to figure out kind of the different knobs, how they can combine in a hybrid way to get the best solution. Before finishing, I want also to introduce another kind of more fundamental, how to say, solution to the temperature problem. Let's remember what I have introduced at the very, very beginning of my talk. We said all of those happening, all those temperature problems happening because voltage is not really scaling down. And we explain it, or not me, this is, as it's very well known in device physics, this is attributed to the fundamental subthreshold swing, which is 60 millivolt per decade at least. And that's attributed by itself to those two capacitances in series. But can we make anything where we push this below the 60 millivolt per decade? In fact, yes, if we could achieve a negative capacitance. Why? Because if you look to this constant factor, the lambda, it's 1 plus something. And as long as this term is positive, we always have higher than 60 millivolt per decade. But if we could make it negative, we could actually make the lambda smaller than 1. And if it's smaller than 1, then we could actually push the subthreshold swing to go below 60 millivolt. But do we have a negative capacitance in the nature? Interestingly, it has been demonstrated that the ferroelectric material, under certain circumstances and certain capacitance matching, can exhibit a negative capacitance effect. That's amazingly important because instead of we have a voltage drop, as we used to have in any two capacitances in series, we have kind of a voltage amplification. As a result of that, we can achieve the same on current of our transistor, but at much lower voltage, as this analysis that we have done at the 7 nanometer FinFET technology. We see here in the red curve, which is the NC FET, how it's a steep, could achieve the same baseline on current at much lower voltage without any increase in the leakage, without any increase in the off current. That means we can operate our circuits at much lower voltage without any loss in the performance. What that really means for neural processing unit? Well, we have recently answered that question, and we did the analysis using the complex framework that I have shown you, and it was using the Google TPU example. And we have shown that the power reduction can be around 40 to 50% in the systolic MAC array at the same performance. And this is all attributed nicely to the reduction in the power that's coming from the reduction of the voltage without a loss in the frequency. Let's remember the Google TPU, or in general the neural processing unit, they have this gigantic systolic array, consume lots of temperature, confined in one small area. If we could reduce the voltage without any loss in the performance, that means lesser power density, and lesser temperature, and that means less cooling cost. Therefore, we could solve the problem fundamentally if we could realize steep transistors or steep subthreshold transistors, such as the negative capacitance transistors, in which performance is not sacrificed while voltage is reduced. This will solve fundamentally the problem. Well, until these breakthroughs or to be adopted commercially, and we see such amazing devices replacing our existing mature CMOS technology, this will take lots of time, and we have to use our traditional solutions such as voltage scaling and frequency scaling, precision scaling. However, I just wanted to tell you there's lots of activities happening in a different research community in device physics and material physicists in order to solve fundamentally the problem. And I personally believe that would be, of course, the best, because this is where we can suppress the problem from where it starts. But it's not that easy, especially when it comes to replacing CMOS technology that is adopted for many decades. Before finishing, I want also to show you an example that instead of fighting against the temperature, and sometimes if you cannot fight against your enemy, why don't you try to live with that enemy? That's also, this concept could be applied for deep learning. Temperature is a problem because ultimately will cause errors. However, neural processing unit can tolerate errors if you train them with errors. That's not easy, but if you could do that, you could actually create deep learning models that inherently resilient against temperature effect. This is a third way to fight against the temperature. So either you will do your traditional solutions that I have explained, or you would go to fundamental solution like replacing your transistor, or if you could not do anything, why don't you live with the temperature effect and train your neural models with respect to temperature effect? That necessitates modeling the errors that's coming from temperature, and then go to your framework where you do the training and live with it, training with it. We have done this work in collaboration with Jian Chen from Dortmund and others, and we have shown that binary neural network, which is one of the new forms of neural networks, they are able actually to survive with errors. If we could model those errors and put them during the training, we see here how the different temperatures did not cause any drop in the accuracy, and this is an example where we could live with the errors. This brings me to the end, and if you are interested in those areas and based on your background, and I know this talk is for the CAS community, so if you are coming from circuit or system, you will find papers from our research group for different perspectives, how to say, starting from device physics, circuit to system. So please take a look, and I'm sure, or I hope that you will find something fits your background. Before finishing, indeed, I would like to acknowledge all our PhD students that contributed largely to this talk. Some of them left, like the analysis that I have shown for the temperature is coming from an old student, Hammam, that he's not, his name is not here, and some of them is here, and also acknowledge all our research partners from outside, as well as the funding agencies. This brings me to the end, and to summarize, first and foremost, fighting against temperature is inevitable in the upcoming technologies. The effectiveness of conventional techniques, frequency, voltage, precision scaling is limited and becoming more and more limited. Advanced on-chip cooling opens doors for new optimizations. Hybrid cooling solution is the key because it will allow us to minimize the cost. If we could not fight against the temperature, maybe we could teach neural networks to live with it. Error-aware neural network training is a key in this aspect. Errors are coming, no, whatever we try to do, errors are coming from the hardware. We have to make our neural networks live with that. There are many different walls facing our technology, and fighting the temperature, we are still at the very beginning. The path and the way is very long. Finally, AI is reshaping the future of humankind, there is no doubt. But the question is, at which cost? Many studies show that training a complex neural network can emit carbon footprint more than not only the lifetime of one vehicle, but 5 vehicles together. Therefore, it's now the right time to investigate how coupling innovations in technology with innovations in architectures can rescue. This brings me to the end, and thank you very much.
Thank you very much for your talk. Thank you so much again. That was a very excellent talk. I have a few questions. Maybe you could shed some more lights on the thermal issues and the thermal profiling that you did, and also how to fabricate the TEC layer. So let's take in parts. So in the slide 12, okay, you have a thermal profile across nanosheets and FinFETs. Can you comment about which tool, which TCAD tool was used to simulate this? And if the temperature profiles in the sheets and the fingers in the FinFETs, if they are basically at the given time for lattice temperature to equilibrate, because these tools can also provide electron temperature, they can provide hole temperature from the electron momentum distribution. So what's the best way to advise our students how to use those TCAD tools?
Okay. So thanks, Sergio. This is an excellent question. And actually, this is one of the very hot topics nowadays in device physics, because the self-heating is really big challenge for sub-7 nanometer devices. Here we have used the TCAD tools from Synopsys, the Centaurus S-device S-process. First of all, we calibrate the TCAD with the measurements, and in this case, we have relied on publicly available data from Intel. And once we calibrate it, then we have to really calibrate all the thermal properties of the material. And that's not easy, but we keep calibrating until we should be able to match the measurements that we have from the devices. So once the calibration is happening and we are able to capture all the physics, including quantum confinement and all other type of defects, then there is a certain method, which is the conductance versus frequency, which allows us to capture, to calibrate the thermal capacitance as well as the thermal resistance. Once this is really happening, we are able actually to get even the thermal time constant, the tau. Therefore, we would be able not only to see the steady state, the static temperature, how to say, which is I'm showing here, for instance, as an example, but also, and more importantly, how long does it take for the heat, for the lattice to be heated up? That is actually, just to give you feeling, I'm sure you would ask that. Nowadays, in the 10 nanometer technology, it's already at the 1 nanosecond, and even several studies show that they could reach a 0.5 nanosecond. That means the time to heat the transistor is getting very small, and this time, then the tau at the area of 0.5 to 1 nanosecond makes even digital circuits becomes already subject to self-heating. And it's in the old days, we used to think self-heating is a problem often only for analog devices, but nowadays even the digital circuits operating in the gigahertz regime, it started to become already subject to self-heating as well. So calibrations needs to be done with measurements, material, and then the only proof is we should see the frequency versus the conductance measurement, the GDS versus frequency. This tells us where it increases, and once we match this from the available data or the data that's coming from measuring the devices, then we would be able to calibrate the thermal resistance, thermal capacitance, and from there we can continue. If this
yes, thanks. Sorry, we have another question coming from Costa Rica, from Jorge Castro Godinez. You know him. He's asking this question to you, Hussam. Basically, besides simulations, have you performed thermal measurements to the actual TPU chip, like the edge TPU, with your temperature measurement setup? That's his question.
Yes, actually, that's actually a good question, and we have just ordered the Google TPU, the edge TPU, to do this measurement pretty much soon. So the answer is not yet, but I'm planning to do this pretty much soon. So the Google edge TPU, we have already ordered it, and we plan to do this analysis.
Thanks. Another question, follow up on the important issue of the, let's say, localized, or let's say, fraction of a chip TC, the thermoelectric cooling layer. That's an emergent technology that's been perfected, I think. And my question is on slide 17, how is the post processing to get the T layer over the chip? So we are familiar with the standard, I think it's slide 17. We are familiar with the standard.
Yes.
Yeah, that's one. Yeah, 17.
Yeah, actually,
With say the conventional packaging. So can you explain more about how to do the post processing after the chip is packaged? How to assemble, the TC layer? How much post process has to do? How stable this process? And why, if you could put over the entire chip, why just put it over, let's say, the most active hotspot? So I imagine that the area you would like to scale as much as possible. So why not do chip-wide?
very good. Two questions, very good. First of all, you will be now surprised that they are actually able to grow up this superlattice layer on top of the silicon itself. So because the superlattice layer at the end is a PNP, so similar material to the semiconductor, therefore they are able actually to integrate it on the chip. And if you look to this picture, or if you look to the original paper from Nature, they were actually, it's not an additional layer, it's within the silicon itself. So on chip cooler. Other people, they have did it, as you said, they did it on top of the silicon. There is advantage and disadvantage for both solutions. And then they integrated inside the TIM, the thermal interface material. So those all will happen in the package, or so I would say in the advanced packaging. So there are two solutions. So you could really grow it while you are fabricating your chip itself. You could do it after that. There is advantage for every solution. Now back to your next question, why don't you just put it on top of the entire chip? That is actually goes back to the main goal that we want to do. We want actually to minimize the cooling cost. So why we would really cover the entire chip and pay large cost for the cooling if we could only cool down where the hotspot is evolving and emerging? So of course, if the entire chip is hot somehow, then why not put the thermoelectric device for the entire chip? But the larger, the more the cost, no doubt. Now, many systems like in complex processors, and even for the neural processing unit, you have a very large area for the SRAM. Those SRAMs typically have very low power density, so you don't really need to cool them down. The best solution, and we also work on this, we have several papers on it, that you build a grid. The grid is you have many thermoelectric devices, and you decide at the runtime to turn on and off whatever you need whenever you need.
Okay. Thanks, Professor Hussam. Another question in your algorithm part for the NPU thermal management. For the thermal management, you adopted precision scaling on the neural network, and as well as frequency scaling. My question is, I think that's addressed in slide 21. Since you're doing frequency scaling, can you mention more about using both the more conventional voltage and frequency scaling? My question is, in this paper, in this study that you have shown on slide 21, are you using also voltage scaling or just frequency scaling?
Okay, in this work, we have focused only on the frequency scaling. However, in other follow-up work, we also looked at the voltage scaling. The reason is, once we touch the voltage, it has a very large impact on the frequency. And that will really kind of screw up the throughput. So we wanted here to be more subtle, and we wanted to not go aggressively to the voltage, because we wanted to keep the throughput as high as possible. However, as I said, in this study, we only focus on the frequency as a knob. In other studies, we looked also to the voltage, but no surprise, once you reduce your voltage, frequency goes down very quickly. And another important issue, those advanced technology nodes, they already operate at 0.7 volt, and reducing the voltage, let's say 0.6 or 5, you start already to be, approaching the near threshold regime. And many problems, if you don't make your design really great in advance, start to appear, and you work in this area for almost a decade.
Yeah, right. Yeah, the throughput heat, the throughput drop is too steep as you go below 0.7. Yeah, indeed. The last question on this middle slide on chip design. In the case of the Intel FinFET, you had to calibrate your SPICE models with some IV data that they published, or did you get the model card? Because I think they're very secretive about those SPICE model cards.
So everything is publicly available. So maybe I should not say Intel 14 precisely, it's calibrated. So in other slides, I wrote calibration. So what we do actually, we look to the available Intel data from publicly available, typically from IDM conference. And then we take these IV characteristics. We go to the TCAD, complex TCAD simulations to reproduce those IVs. And once we have those calibrated TCAD, then jointly with the BSIM group, we develop the calibrated compact model, the calibrated SPICE model, how to say. Then we moved and we characterize the entire standard cell library using this calibrated compact model. And once you have the cell library, then you can continue with the chip design. So the whole procedure, we explain it in the paper and other related papers, but this involves calibrations from device to SPICE to libraries, etc.
Very interesting. Very interesting. Well, just to close, we are about 10 minutes over time, but it's very interesting. You touched so many grounds and topics. We are thankful for you. Basically, on the negative capacitance, FET. Okay, in slide 29, you mentioned that the advantage of having a steeper slope on subthreshold. But it seems to me that still they have not got the red curve in this picture, having the same ion current as the conventional FinFET, the blue curve, and that's a problem that has been plaguing, hindering the adoption of those transistors, just because the ion current does not go as high as we'd like to. So what's the status of this development for the negative capacitance FET, which is I know you've been working in this subject for many, many years and published, very important work on this. But from the device side, are they getting good enough ion from actual devices?
Actually, with respect to NCFET, they are getting very good ion. Even some of them, they showed an 2x improvement on top of the original ion. So this is amazingly good. The problems with the NCFET, and it's actually how to get the device without hysteresis. And this is not easy because the steepness of the slope that makes it really not easy to get hysteresis free. Also, all the underlying physics is still under debate, and whenever you don't fundamentally understand what's happening, then it's also difficult. Another challenge is if you really want to adopt those emerging technologies, you really need to ensure their scalability. And having a very thin ultra-thin ferroelectric device, ferroelectric layer, in which to allow the scaling, then there is a debate about if the negative capacitance effect could really still exist in 1 nanometer or 2 nanometer. There is an amazing work came from Sayyid from University of Berkeley 2 years ago, or 1 year ago. He also showed that what has been believed for a long time, that the ferroelectrism does not hold or will be lost at the very thin layer, could still work with lots of material engineering. So this is the biggest challenge. It's the on current is doing well. The hysteresis free is very challenging. Having a very thin ferroelectric layer is not easy. And nowadays there's lots of investigations in not in CFET but ferroelectric device for memory. So this is a very active topic I did not talk about. But also nowadays, also even from logic, they talk about, let's have it as a better high K layer, high K gate, not necessarily to be super, negative capacitor effect, but at least, a better high K to have a better capacitor and a better electrostatic integrity.
Okay, thanks, Professor Hussam Amrouch. Thanks very much for being here with the IEEE Circuits and System workshop in South Brazil. That's organized by our CAS chapter in Rio Grande do Sul state. I hope to see you again, all of you who are in this workshop. Remember, at 1:30 p.m. Today, on September 29, 2021, at 1:30, Jorge Castro will be working on accuracy for energy trade-off and approximate computing coming to the, let's say, rescue to energy efficiency. And so he'll look at this design paradigm of approximate computer. That's at 1:30, GMT -3. Brazilian time is going to be 6:30 p.m. Europe time, Central Europe time. Thanks a lot, Hussam, on behalf of the organization. I hope to see you again. That was very, very nice talk. All our students here in the chapter really appreciate. And last words for you.
Thanks a lot, Sergio. Thanks for all the organizers. It was a great pleasure. So I hope you enjoy the remaining of your workshop. Thanks for the nice.
Yes. We'll have 3 days more. That will run Thursday and Friday, 2 days more. So please come back at 1:30 to listen to Jorge Castro Godinez on his talk on approximate computing. Bye. Have a nice one until next section. Bye. Thanks, Hassan.
Sure.
Okay, so everyone, thank you very much for being here for this presentation or this night presentation. We end here our morning presentation. So I'd like to thank Professor Bumpy for being the session chair. And I'd like to remind you that we will come back at 1:30 this afternoon. Yeah. 1:30 this afternoon, and stay tuned that we have a lot more interesting talks. See you in this afternoon.
See you then. See you 1:30 p.m. Bye.